Dear friends, today I will discuss with you the Thevenins Theorem. First of all, what is the use of Thevenins Theorem? Actually, Thevenins Theorem, it is an important, you can say it is a tool. It is a tool to avoid the lengthy and difficult calculations about linear circuits, or in case of the network. So it is, Thevenins theorem actually it is a tool, simple method for analyzing a network. So consider a network like this is our voltage source, then we are having impedance Z1. Impedance means resistance or inductance or reactance, and second impedance is Z2, and third one we are having Z3. So this is a type of the network, and here actually it is a load impedance ZL. One thing note down, this is not the simple circuit, because how you say about whether about Z1, Z2, whether they are in series or in parallel, Z2 and Z3. So that's very difficult for simplifying this circuit. So therefore we are going to the Thevenins theorem. This is ZL. Now we are having here the loop number 1, and in this loop some current is flowing. Let we call it I1. Here the current flowing is I2. There are two loops in closed paths. Now equivalent to this network, we are having a very simple Thevenin, simplified circuit. Voltage source V dash different from V, Z impedance different from Z1, Z2 and Z3, but ZL it is the same. And current flowing is I2, which was in the second loop. The question is, what about the value of the V dash, number 1? What's the value of Z, number 2? Number 3, what is the value of I2? Now we're going to solve for these three unknown quantities. So first of all, I'm going to write the Kirchhoff voltage law in the loop number 1. That's very simple. You know very well that voltage is equals to current into the impedance I1 Z1 is I2 Z2. Now note down one thing, while traversing this path, you are going along, we are traversing like this. So I1 is flowing according to as we are traversing. But I2 is flowing in opposite in direction to the direction which we are traversing. We are traversing downward, and I2 is flowing upwards. So that's why this impedance I1 Z2 will be positive, but I2 Z2 in this impedance, for this impedance, for this current I2, the impedance I2 Z2, that is the voltage, that voltage will be taken as negative. I1 Z1 voltage taken as positive because current flowing as we are traversing, but I2 flowing along in opposite direction. So this voltage I2 Z2 will be taken as negative. So I1 minus I2. I explained the reason why minus I2 into Z2. So V is equals to I1 Z1 plus, open the bracket, solving for I1. Okay, this is equation number 1. Now we're coming to the loop number 2. Kirchhoff voltage law for loop number 2. And here there is no voltage source, that means 0. Z3 I2, ZL I2, okay. But we are traversing I2. So I2 Z2 is taken as positive, but I1 Z1 is opposite in direction, so taken as negative. Okay, it is clear why I1 Z1 is taken as negative, that voltage, because it was in opposite direction I1, as we were traversing along the path according to I2. Open the bracket and find the value of I2. They are combined, I2 parameters, I2 combined, and then minus I1 Z2. Okay. Now then I1, the value of I1 becomes from this equation divided by Z2. So this is the value of the I1 in terms of I2. Now what we do, we substitute this value in equation number 1. Substituting I1 in equation number 1, the voltage V becomes then here, I1 is here, substituting here. Now rest is the simplification. You just see how I am simplifying. I think you will follow. Easily. There's no problem. Very simple calculations. Again simplifying. Vz2 divided by, because I2 from right hand side is taken as common. This is Z2, sorry. Z2 plus ZL plus Z3 minus Z2 square. Now I2 becomes equals to dividing numerator and denominator by Z1 plus Z2 of the right hand side. Dividing numerator and denominator by Z1 plus Z2. Now from the denominator, open the bracket. Just go for multiplication. And note down here Z2 square cancels out. And Z1, Z3, they can be combined. Z3 is common, Z1 plus Z2. Similarly, here Z1, Z2 plus ZL is again taken as common. There was 2 terms for ZL. Now each divided by Z1 plus Z2. Okay, each divided by Z1 plus Z2. Z1 plus Z2 then cancels out. And the value of I2 becomes So this is the value of I2, very, very important. Equivalent current for Thevenin equivalent circuit. Now next, how to find the open circuit voltage. Now think of it, V dash. To find the open circuit voltage, between point 1 and 2, we are disconnecting ZL. ZL will be disconnected. So that means 1 and 2 becomes the open circuit. When it is open circuit, no current will flow, I2 will be 0 then. Now no current flowing in the second loop because it is open circuit. So only current flowing is I1. And we find the value of V dash between point 1 and 2. What is the voltage between 1 and 2? That is called the open circuit voltage. Now this is only single loop. And from here you write down the Kirchhoff voltage law. Very simple. That means V equals to I1 Z1 plus Z2. From here you find the value of, I1. This is a closed loop and write down the Kirchhoff voltage law. Now we find I1, it becomes V upon Z1 plus Z2. Now then, what is voltage across Z2? That is V dash. V dash is voltage across the Z2. Because open circuit voltage substituting I1 here. So V dash, which is across the Z2, that becomes, and this open circuit voltage V dash. So it is required for the Thevenin equivalent circuit. So open circuit voltage which is required to Thevenin equivalent circuit, it is Z2 upon Z1 plus Z2 into V. So this is open circuit voltage. Now we left only a single parameter, Z. What is this value? We know already I2, we know already V dash, only Z we have to find now. Now equivalent impedance, what is Z value? This is a problem. Now again coming here, to find the Z, all the voltage sources are replaced by a short circuit. All voltages will be shorted. Okay, now we are going to short this. Connecting this line means shortening. So now there is no voltage source. Now we have to find between these 2 points what is the total impedance. This shortening, we have to find between these 2 points the impedance. Now here that is the impedance Z. Z we have to find. Okay, which is in the box, dots, and this is ZL. So Z, what is the value of Z? Just see now Z1 and Z2 are coming in parallel, and then they are coming in series with Z3. Z1 and Z2 are coming in parallel, and then they are in series with Z3. That becomes the value of Z. So Z1, Z2 mean the parallel combination is Z1, Z2 upon Z1 plus Z2. This is a parallel combination. Now because it is in series with Z3, so this is the value of the Z, okay, which is required for the Thevenin equivalent circuit. Now the Thevenin equivalent circuit is complete. We know the equivalent impedance for Thevenin network. Okay. Now lastly, we're going to draw the equivalent circuit and the values. This is a V dash. We already know the value of V dash. What it is? It is, VZ2 upon Z1 plus Z2. This is Z, we already calculated it just above. This is the value for Z. Now then, here we are having the ZL. Now the current flowing I2 already I calculated. Okay. I2, or we just see, you may call it I now. I is equals to now one thing is very interesting. If you independently write down I, how you write? I is equals to whatever this voltage source, which is V dash, and V dash is VZ2 upon Z1 plus Z2, this one, divided by the total impedance of the circuit, which is Z plus ZL. Okay, ZL is here, and Z. What is Z? Just calculated above. Okay, it is just calculated above. So, which is Z3 plus Z1, Z2 upon Z1 plus Z2. Okay, now this total, this current I, which I have written using this circuit, this current is the same as it was calculated above, which was called previously I2. The same was the I2. So that means our circuit is exactly okay. Thevenin equivalent circuit. So it's very important for Thevenin equivalent circuit, you find always V dash using this formula, Z using above, and current using this formula. Okay, thank you very much.